Have you ever wondered how Java programs run on Windows, Mac, and Linux without changing a single line of code? And have you ever asked yourself who cleans up all the objects we create using new? In this video, we will understand how JVM works internally, how memory is managed, and how Java garbage collection evolved from simple serial GC to modern collectors like ZGC and generational ZGC. Here is our roadmap. First, we will understand the JVM architecture. Then, we will dive into garbage collection and see why new GC algorithms were introduced over time. Finally, we will learn how to enable and analyze GC logs, which is one of the most important skills for Java backend engineers who are working in a production. What is JVM? Let's see an analogy. Think of JVM as a language translator. Imagine you wrote a book in Tamil. People in Japan and Germany can read it only if they have a translator. Similarly, Java code is compiled into bytecode, and then JVM translates that bytecode into machine instructions understood by the operating system. This is why Java follows the famous write once and run anywhere principle. We compile our .java file into .class bytecode using the JavaC compiler. That bytecode is then executed by the JVM. The JVM hides all operating system differences from the developers. That's the magic behind the Java portability. Let's see about JVM core components. Think of a restaurant, receptionist or the class loader, dining area or the runtime data area, chef or the execution engine. When a customer enters a restaurant, the receptionist guides them. Similarly, class loader loads the required classes. The runtime area acts like the restaurant space where everything happens. Finally, the execution engine is the chief that actually performs the work. Together, these three components form the heart of JVM. Let's see about class loader subsystem. Imagine a movie theater. Before movie starts, movie file is loaded, quality is checked, projector is being prepared, movie begins. The class loader works in three stages. First is loading, where the class files are brought into memory. Then comes linking. The JVM verifies the bytecode, allocates memory for the static variables, and resolve references. Finally comes initialization. Static variables receives actual values and static blocks are executed. Only after all this is the class ready for execution. If you have ever seen a static block execute before main, this is the reason. Let's see about runtime data area. Think of a company office. The heap is like a shared warehouse. Everyone in the company can access it. All objects are stored here. Stacks are like personal desks assigned to employees. Each thread gets its own stack. Method area is like company's documentation shared by everyone. PC registers are the bookmarks that tell each thread where it currently is in the code. Understanding these memory areas is critical because most performance issues happen here. Let's see about execution engine. Imagine learning a route to work. On our first day, you will use Google Maps every time. That's the interpreter. It reads instructions one by one. After taking a route daily, you memorize it. That's the JIT Compiler. Frequently executed code is converted into optimized native machine code. This makes Java programs much faster over time. And while all this is happening, the garbage collector keeps cleaning unused objects from memory. Now comes the most exciting part, garbage collection. Every GC algorithm in Java exists because the previous one had some limitation. Let's see how Java GC evolved nearly over 30 years. Let's see about serial GC. Imagine one cleaner cleaning an entire shopping mall. Serial GC uses a single thread. One worker cleans the entire heap. While cleaning is happening, every application thread must stop. This is called Stop the World event. It worked well in 1990 when machines had single CPU core. But as applications grew larger, one cleaner was no longer enough. One cleaner, one broom, entire mall. This is the serial GC. Let's see about parallel GC. Instead of one cleaner, imagine 10 cleaners cleaning simultaneously. Parallel GC solved the biggest weakness of serial GC. It uses multiple threads for garbage collection. Application still passes during GC, but cleanup finishes much faster. Its primary goal is throughput. In other words, maximize the amount of useful work done by the application. Parallel GC was the default collector in Java 8. Let's look into CMS GC. Imagine cleaning a house while people are still living inside it. CMS introduced a revolutionary idea. Instead of stopping the application for long periods, much of the work happens concurrently. The application continues running while GC works in background. This significantly reduces the pass times. However, CMS had major issues. Memory fragmentation, floating garbage, and high CPU overhead eventually lead to its removal. CMS made passes shorter but made memory management more complicated. Let's look into G1 GC. Imagine a city divided into 1,000 small neighborhoods. Instead of cleaning the whole city, the government cleans the dirtiest neighborhoods first. G1 stands for garbage first. Instead of fixed memory regions, Heap is divided into many equal-sized regions. The JVM tracks how much garbage exists in each region. Then it cleans the region with the highest garbage percentage first. This gives more predictable pass times and eliminates fragmentations through compaction. That is why G1 becomes the default GC from Java 9. Let's see about ZGC. Imagine road repairs happening while traffic continues moving. ZGC takes care concurrency to the another level. Almost all GC works happening while the application keeps running. Pass times stay below 1 millisecond even with terabytes of memory. This is achieved using innovative techniques like colored pointers and load barriers. For latency-sensitive systems like trading platforms, gaming servers, and large-scale cloud services, ZGC is a game changer. Heap size grows from gigabytes to terabytes, but pass times remains nearly unchanged. Let's look into Shenandoah and generational ZGC. Two different engineering teams trying to build the fastest sports car. Shenandoah and ZGC have the same goal, ultra-low latency. They simply use different engineering approaches. Shenandoah relies on forwarding pointers. ZGC relies on colored pointers. Then came generational ZGC in Java 21. Engineers realized most objects die young. So why scan everything equally? Generational ZGC compares young and old objects, leading to significantly better throughput while preserving sub-millisecond passes. This is why many engineers believe generational ZGC is the future of Java GC. Let's look into GC comparison table. If you are confused about which GC to choose, remember this shortcut: serial GC for small systems and parallel GC for maximum throughput, and G1 GC for general purpose production workloads, and ZGC for lowest latency, and Shenandoah GC for lowest latency alternative for ZGC, and generational ZGC currently the most balanced option for large modern applications. Let's look into GC logging. Imagine taking your car to a mechanic without diagnostics logs. They are just guessing. The same applies to the Java performance. Without GC logs, troubleshooting becomes guesswork. GC logs tells us exactly what the JVM is doing with the memory. Why GC logging? GC logging answers critical production questions. Why are user experience slow responses? Why is memory continuously growing? Why did a full GC happen? Why is throughput is dropping? GC logs provide the evidence needed to answer these questions. If you are working as a backend engineer, GC logs are often the first thing you will inspect during the performance incidents. Java 8 logging. Before Java 9, GC logging was messy. Multiple flags were required. Different collectors produced different log formats. Remembering all these options was very difficult. That is why Java introduced unified logging. From Java 9 onwards, here comes the unified logging. Imagine replacing 10 remote controls with a single universal remote. Unified logging is simplified everything. Instead of dozens of logging flags, we now use a consistent -Xlog syntax. Needed heap details, use GC plus heap. Needed GC faces, use GC plus faces. Need everything, use GC star equals to debug. Much cleaner and easier to maintain. These are the key metrics all you want. When analyzing GC logs, focus on 5 metrics: pass time, frequency, heap after GC, throughput, and promotion rate. These are the 5 numbers reveals the most JVM memory problems. Easy memory trick. Think of them as a vital signs of JVM health. Here are the key takeaways. Let's recap. The JVM consists of the class loader, runtime data area, and the execution engine. Garbage collection evolved from serial GC to generational ZGC over nearly 3 decades. For most applications, G1GC is the great default choice. For low latency systems, look at ZGC or Shenandoah. And most importantly, always enable GC logging in production. Which garbage collector are you currently using in production? G1, ZGC, Shenandoah, or something else? Let me know in the comments. And if you found this explanation useful, subscribe for more Java, JVM, system design, and backend engineering content. Thank you.